And we're live. Hello, Matthias. Hello, Palash. Let me know how you like the background music, if the volume is okay. Can try another one as well. Hello, welcome back. Hello, Sumera. How's everyone doing? Having a good Friday? End of the work week, I guess, for most. Almost summer in Berlin. Indeed. I think the weather is not going to be quite as nice next week, though, so we should savor it while we can. But right now, for the next hour or two, we'll optimize some code. All right, I guess we can get started. Awesome. Let me know, Matthias, if we should ever change the volume or something about the background music. But I think it should be okay. All right, let's try this thing. I guess I'm actually going to open the second screen and drop that over there. All right, thanks for letting me know. I will increase the volume a little bit of the background music. All right, so here's what we're going to be doing today. So we got a couple of reports that CPU usage can be high in these code paths. So to kind of explain what this does in the Parca agent, and more generally what the Parca agent does, So the Parca agent is what we happen to use at Polar Signals and with our customers, as well as within the open source community. This is an entirely open source project. And the Parca agent is what captures CPU profiling data. So this is the agent that we deploy on every single host, on every machine, and it starts profiling everything that is on that machine. And this particular piece of code that we're going to be looking at today is using something called perf maps. So for normal binaries, let's say something written in Go or in C or in Rust or in C++, anything that kind of compiles to a native binary, we don't need this particular code path, because those kinds of applications have something called debug infos that kind of, on a high level, map a memory address to a function name, so that we as humans can actually understand what this profiling data actually represents. Because the raw data that the Parca agent actually captures is just memory addresses. So all we see is memory address 1, 2, 3, 4, 5, and we can get that entire stack. But we only essentially get that address, or also known as program counters. And in the typical case, we use the debug info to translate this. But there are cases, and in this particular code path is exercised for just-in-time compiled languages. So something like Java or Node.js or Erlang or Julia, where the code is not compiled ahead of time, but it is compiled on the machine. And that can be done for a variety of reasons. It can be that it gets recompiled at runtime. That's what the Java hotspot VM does. It figures out where the hotspots are and kind of tries to keep optimizing that code there. But because in that kind of scenario, we don't have a predefined mapping of memory address to function name, we need some other way to be able to do that translation. And that's what one of the things that can be used for this is called the perf map. And we have an example of a couple of perf maps here. So for example, we have an example of a Node.js one, and the way that looks is that we have the kind of address range. So this is a sorted list. So from this address to this address, everything is represented. Everything in that range is this function, the writer function in REFL.js on line 514. So this is something that just-in-time compilers write out to kind of a standardized location, and then profilers, just like Parca agent or just regular old Linux perf, can use this to then understand this mapping, right? Because it's just in time compiled, we don't have that mapping ahead of time. We actually need to look at it on the host where it was just in time compiled in that particular setting. So, and we've essentially had a couple of reports that this has been using too much CPU, and we saw some profiling data that kind of shows that this is true. Unfortunately, our own production environment doesn't use any just-in-time compiled languages. That's why I can't show any production profiling data today. But luckily, we already have benchmarking tests in this repository for this particular piece of code. So I'm going to start optimizing the same way as we kind of always go about it from the methodology perspective. we're gonna run our benchmarks now. Then we're gonna try to see what we can optimize about this code, and then we're gonna keep iterating on this to see if we're making progress and making the code faster. So, without further ado, my typical benchmarking command I already have in my history. So just to make sure that we'll have enough statistical significance for comparing benchmark results, we're just going to run this with 10 times so that we gather enough data for statistical significance. And this also means that we'll have some data in our CPU profiling data. And actually, I would like to, let's just run this one more time. I actually want to save all of these separately, old CPU and old text. So this is going to be our baseline. We're going to start with these numbers, and now we're going to have a look at what can we improve in this in these code paths. To start, what we're going to do is we're going to have a look at our profiling data for this. That just opened on my other. I forgot I can't do full screen stuff on the stream. I just need to do things like this. All right, so let's have a look. So let's expand just the part where our benchmark is running. All this other stuff that we're seeing here, this is just system stuff that's happening. We're not really interested in that just yet. We want to see what is it that our benchmark actually runs, and it's almost entirely, we can see there's some error checking here, but that's not something that we're interested in optimizing. So we can focus on just everything that happens in this read map function. So we can see pretty considerable amount is spent doing string splits. That's already a good starting point. This is going to generate new strings. We can definitely see if we can maybe avoid doing this. Maybe we can just read parts of the string without actually splitting it. We'll see what exactly the parser does that we have here. We're parsing some integers, we're sorting stuff, we're growing a slice. So maybe there's an opportunity for pre-allocating this slice so that we don't need to keep growing it as often. We're using a scanner.text. This seems to do plenty of memory allocations. So what we're seeing here is it's converting a byte slice to a string, and essentially what this does is it's reading the underlying file and converting the byte slice that it's reading into text. I suspect this isn't going to be 100% necessary because we're already parsing these strings afterwards anyway. So we may be able to kind of get around this and don't have to do these string allocations. So if we're only reading the byte slice and directly parsing these integers out of the byte slice, because that's kind of think back to this test data. Probably what we're parsing here is this this address, and we're reading the whole line. Yeah, probably that's what's happening, and we're doing multiple copies of several of these strings in order to be able to parse it. It's likely that that's not necessary to do. Let's see. Last but not least, buffer.io scanner.scan. So this is something that helps us kind of read the file line by line, and I imagine that there may be opportunities to read this in a smarter way, because I believe a scanner always allocates new memory for every line. But we can have a look at the internals of what each of these do. I can go back to the Matthias had a couple of questions. So we had a question of what's the second column. I'm actually not 100% sure what the second column is. We'll see. We'll hopefully see in the code what the second column is. And the first one is the address. You're absolutely right. So the first one is the address. Then I'm not sure what the second one is. Then it's the function name. Then it's the file and line number. So let's have a look at the code. Maybe the code tells us some more about what this data is that we're seeing. And by the way, let me know if the font size is ever not large enough. I can certainly still increase this. So what did we say? Our function name is read map. So we have a file system, and we're reading a file from the file system. It's just like what we expected. We're using a scanner, just like we expected, to read line by line. I wonder if scanning will always allocate. Let's see. Searches for the next token. We're copying data to the buffer. Making sure that we actually read everything until the delimiter. All right. And then the other function that we were using here is the s.text. I want to say there's also, there's s.bytes. So maybe we can actually continue using the scanner, but instead use bytes instead of that. Bytes returns the most recent token generated by a call to scan. The underlying array may point to data that will be overwritten in subsequent call to scan. It does no allocation. That's exactly what we're looking for. Matthias was saying Vim size is great. Maybe the profile is a bit too small. Are you talking about the like myself? Matthias? Let me know. I see that okay. Thanks for letting me know. I'll try to increase this font for this. Yeah, that makes sense. Thanks for letting me know. Yeah, makes sense. Hopefully this is better. So then let's quickly go over this one more time, what we were talking about earlier. And we can see this now already, right? We can see we have our string split, so we're splitting the line into multiples. Then the first thing, here we have our answer to what the second column is. It's the size. So the start address and how much of this address space are we covering with this particular function. So everything in that range will map to that function name. And then we just keep adding to adders, which, like I was saying, looks like we're not pre-allocating anything just yet. Probably worth doing, at least so that the first couple of slice growing we can save ourselves. Maybe we can make this, you know, some multiple of 2, maybe, I don't know, 256, 512, 1024, something like that. I expect if we find these files, they're going to have quite a fair amount of entries. So pre-allocating by some number is probably worth it as a trade-off. All right, let's see. What else are we doing? Looks like we're doing more. I don't know, did we see trim prefix in the profiling data? This is an interesting one because I don't see it. But trim prefix, I'm fairly certain it might cause an allocation. I'm not sure if this actually causes an allocation. I'm honest. It might not. It may do an allocation, it may not. And then we're parsing the size, and we're just doing a check. All right, I think I have a good idea of what we can do with this. So first things first, let's do some pre-allocation here, because we saw that growing the slice is something that we see quite often. So we can already I've already forgotten what the previous data looked like, so let's have a look. Oh, looks like that actually made things worse. So probably 512 was actually too much. Here's the mistake. We didn't pre-allocate, we just allocated a large slice and continued to append. So let's rerun this with what we actually wanted to do. Small, subtle mistake. Definitely one that I've done before. Matthias was giving us a tip in chat. From Dave Cheney's blog, I learned that piping into new text lets you write into the file and read from terminal right away. Let's do that. Let's do that together. How would we do that? Is it just like this? Yeah, looks like it. Thanks for the tip, Matthias. And just double checking real quick that we actually did write to this file. 13, yeah, looks like that's exactly what happened. Cool. You live and you learn. All right, so now hopefully we got an improvement. Still no improvement. All right, then let's pre-allocate a smaller amount. Allocating too much. All right. Okay, maybe this is the wrong avenue to explore at this point. We can try one more time, maybe 64 instead. Shout out from Matthias to Dave Cheney. All right, let's see. Okay, finally we have a small but sure improvement. All right, we can continue to maybe try and tweak this as we go along, but it seems like this is not going to be where we're going to get a huge improvement anymore, but we can already check our new profiling data. Oops, this opened in my other browser. Over. So, but as we can see, now we're spending more in make slice as opposed to grow slice. I can't even find grow slice anymore. Perhaps 32 was still, sorry, 64 was still too large. But we got an improvement. We can barely see that part. Let's try to continue with some of the ones that are represented larger here. So maybe we can start with string split, and we can maybe combine this together with text. So what we're gonna do is we're gonna take our bytes instead of, GitHub Copilot already knew where we were going. So, and we're gonna search for our occurrences of white space of strings, of spaces in here. So first space. All right, so that means Copilot is on the right track. This is incorrect. It's bytes dot index. It's not always correct and doesn't fully know how to. What are we searching for? All right, now we got it. All right, so we're searching for our first space and using our first space. I actually kind of like this, what GitHub Copilot is suggesting. So what we would do is, instead of kind of chunking it up each individually first, what we're going to do is we're going to first find all the occurrences of spaces, and then we're going to actually kind of read each individual part. So we're going to find the second space. And finally, we're going to read our third space. Yeah, okay. So because what we're doing is we're gonna keep searching by slicing our byte slice. That's why we need to always take the offsets that we're finding plus the space that we're skipping in here. So now we've got all of the pieces that we actually want. And now we can slice it in the way that we desire. So maybe we can name these just so it's a bit easier. We're going to have our address. That's our space from the beginning until the first space, right? We're going to have a look. You can name these address bytes, size bytes. That's not quite right. That's first space plus 1 to second space. And then what do we call this? Not a huge fan of not naming the fields, if I'm honest. We just called it symbol. Okay. And here we called it end, so we're going to need to do some calculation here. It looks like we did here as well. We got a question in chat. If we can have that bytes.index in a func and pass the indexes, and byte and search string would be much more readable. Let's see. So let's see. How would we do that? Are you thinking something like split line with our buffer, then we return a map line, say header. Are you thinking something like this, Nikilesh? Let me know. Sorry about that. I think I just removed it. Maybe you can see it now. Maybe I can blend the comments in a different position. Is that possible? Still learning about Restream. Let's see. I'm gonna blend Matthias in here. Unfortunately, it doesn't look like I can do that. But I'm definitely gonna remove, oops. But I removed it now, so let me know if this is roughly what you were thinking. So we would have a split line function, and then we return a perf map line, maybe a parse. No, just a perf map line, and then oops, I jumped. So the idea here was that we're going to pass in our buffer and we're going to return our perf map line. But I guess what we could actually do is we could directly return this map adder. I think we're not going to be doing a whole lot more in here. But please leave more suggestions in the comments. All right, then let me, what's this called? And then last thing is symbol bytes. Did I miss something? Adder bytes, size bytes. Did we even do a third one? Actually, what split n does is it splits it into n pieces, right? At most n substrings. So actually, we're only searching for 2 spaces. So this is all we're looking for. And then we can copy some of this down here. We need to do some fixing, but essentially all we're going to be doing here is pass this, and maybe we can call this parse perf map line. And yeah, of course, we're going to need to turn an error here, and that already means that we can't do this anymore. But line, comma, error. Returns. All right, so now that we've kind of moved this out of this function, I do agree this is quite a bit more readable, which is quite nice. Now we can focus on this part. So we want to trim this 0x prefix because as with all standards, not everyone implements the standard in the same way. So we've seen occurrences like this one. This is produced by the Erlang VM. We get an address that is prefixed with 0x, or as we saw previously, the Node.js example is not. So should the symbol bytes index start from second index plus 1 rather than first plus second plus 2? So I believe the way that we implemented it, let's have another look. So what we're doing is we're searching the original byte slice. Let me blend in this question real quick. So Nikilesh, and let me know if I'm butchering your name, by the way, was asking, should the symbol bytes index start from second index plus 1 rather than first plus second plus 2? So I think we're doing this correctly here, actually, because what we're doing is when we search for our second space, we're actually already slicing the byte slice so that we're only looking at everything after the first space that we've already found. So if that, in 4 indexes from that position onwards were to be the next space, that would mean that we need to start from that position, right? So we need to actually, I do think we're doing it correctly, but hopefully unit tests are going to tell us if we've made a mistake later. All right, so this is telling us that we don't have L anymore, so we have adder bytes. We cannot pass a byte slice, of course, into strings.trim prefix. Lucky for us, there's actually a bytes.trim prefix. And we need to pass, of course, a byte slice. And then it's expecting us to pass a string to parse uint. Let's see if there is a function for us to pass a byte slice in this, actually. I want to say there is not, but parse int. What's this? Oh, it also wants a string. There's something that takes a byte slice in this package. Looks like not, but maybe there's something that we're not thinking of. What are we searching for? Golang parse int from bytes. Aha, of course, this makes sense. But how do we know which byte order is being used? What does this function do? Whoops. Parse uint. I suppose it uses whatever the platform uses. So what we're gonna do is I'm gonna check out this and system. I want to say there was something in the Go standard library that gives us the system's endianness. But otherwise, I guess we can copy this hack. What did this again use? Anyway, we can also check first by converting this to a string, and then we can worry about it later. it's into the wrong position. And if this string allocation actually still causes trouble later, we can then worry about it. And then we're gonna do string size bytes. This one's the whole line, so what is that? Then it's just B. I think in the error case, it's fine for us to do some allocations. Things have already gone wrong anyway. So we've got our start, our end, and our symbol. And in this case, we absolutely do want an allocation, because remember, when we looked at this function, it told us that the underlying array may point to data that will be overwritten by a subsequent call to scan. It does no allocation. So in this particular case, we actually do want an allocation to happen, which in this case, the allocation is that by doing this string of the symbol bytes, it will actually copy the underlying byte slice. So it is actually safe for us to do. All right. I believe, let's check. Whoops. Not want to modify anything here. Let's check that our tests are still working. Okay. Looks like it is not. Runtime error. 107. Aha, I see. What we're doing is something that just doesn't make any sense. We want to slice it from 9 to 3. That just doesn't make any sense. So what we're going to need here is first space plus 1 plus second space. All right, our tests pass. So let's run our benchmarks again. All right, I want to say that's already looking pretty good. I want to say this is already less than what we were seeing before. But let's compare the improvement. All right, cool. So we're seeing almost a 20% improvement already. That's awesome. But let's have a look at the profiling data. All right, so we can see that now the majority of time is spent in parse perf map line and scanner. Okay. Still quite a bit of time in the scanner, so maybe there's something there that we can improve. And then parse perf map line, slice byte to string, of course, that's something. And then converting to the integer bytes.index. We're not going to get around this one. We're always going to have to search for the spaces. Trim prefix, that's fine. What checks that it has a prefix, but yeah, okay, that's fine. Slice byte to string, slice byte to string. So then I would say let's instead try not to cause an allocation here, just like we were saying before. So Let's have a closer look again at what this thing does. So it parses an integer for unsigned numbers. And what is the thing that we actually return here? You return n. So n is the thing that we keep modifying in here. I have to wonder, I see why this is. So this is a little bit more complicated than what we're looking for, because we can specify the base as well as the bit size. But we actually know exactly what we're looking at, and that's why we can actually use the byte order packages. So now that makes sense. Now we just need to figure out have a look and search for kernel perf map interface. Our hex numbers without zero. So it looks like Node.js even implements the specification entirely incorrectly. It says without 0x, but Node.js does. No, sorry, Erlang implements it this way. Our hex numbers. Wait a second. That means we do actually have to use. Yeah. The little endian and big endian are not going to be helpful. Okay, then I have an alternative proposal. We are just going to copy this function. And if it helps us get a large perf improvement, we can keep it. Did we call it? Parse. So. And we do know for a fact that it's case. Maybe we can find something that Golang parse exclude. What are these folks doing? Okay, they're just using parse uint. All right, then Don't know where syntax error function here. Oh. Do this. It's something that we can reuse maybe. All right, nice. So strconf. Oh my, okay. Okay, they wanted to use strings.clone instead, but they cannot because it would be a transitive dependency. Okay, but we can. So and here. Okay. The way around this time. Okay. Thanks for letting me know, Matthias. I'll make sure to do that next time. All right. The lower function. Oof, it's quite a bit of things. Base error. Hopefully this gives us actually a good amount of improvement so that we're not doing this for nothing. But that also happens. Size. And I think I already saw max event as well. Let's get the rest over of all the definitions, maybe. Bit size error, range error. Slides this, so we need to make sure we apply everything consistently. In all the error cases, we can go the slow paths. That's all right. in those cases, things have already gone south. Untyped string custom pilot. 58. Make a distinction here. String, function and string. All right, now we're almost there. Range error and underscore. Okay. All right. Underscore. Okay. Underscore. Okay. All right. Oops. Parse you in 115. Change this to byte slice as well. Okay, finally. Passing test. Oh, we actually need to make use of it. All right, now. New. All righty. I want to say that already looks a little bit better again as well. Let's see. Previously, let's scroll up. It's been a while, but we saw about a 16% improvement. We saw another 3% improvement by removing these allocations. That's awesome. All right, doing well. Now, let's have another look at the profiling data. We can see that in our function, we're now spending most of our time in searching for the index. We're always going to need to be doing that. We are trimming the prefix. You know, if we have it, we will always have to do it. We always will have to parse the integer, and then this allocation is appears. Actually, we're now going to have to pull up the Go tool pprof because I want to see something very specific. I'm going to increase my. Unfortunately, this is a feature we have not implemented in pprof yet. What I want to see is what was our function name? Read map. I want to see the parse perf map line. Yeah. So we're spending some time in this. Okay, interesting. $330 in this one. That's an interesting one. I didn't expect that. But let's move on. We know that we're gonna always have to search for the indices. Now, and here is the big memory allocation. So good news is this is truly the only time that we're doing a string allocation. Thanks for the shout out, Nikilesh. Yeah, I mean, this is kind of what performance engineering is all about, trying to truly understand what's happening and making the best of it. And sometimes it's worth it, sometimes it's not necessarily. Yeah, you hit the nail on the head. The question, how maintainable is it when you rewrite internal functions? So, I mean, what we saw here, this is parsing a hex string. This is not something that changes very often. If this was something, parsing a struct in the Linux kernel or something, that would be much more brittle. But with this particular case, I'm not actually very worried that this will ever break, right? Worst thing is that we're maybe missing an optimization that upstream might do that we're not doing, but turns out we actually just did exactly that for ourselves, right? We can probably go in and optimize this even further, because as we saw earlier, this actually handles various cases. It handles, base 10, base 16. You can pass whatever base you want. In reality, this is actually sorry, this is the underscore OK function. This particular this parse UN function that we have here, it's very generic, right? We actually don't need it to be this generic. So the next step would actually be simplifying this, and that actually would make it more maintainable again, because we would only care about one very specific case. Looks like there are a bunch of cases here, right? It does a whole lot of things to check and do things about parsing different kind of bases. So probably we would want to kind of rewrite this again and write it in a way that we only care about parsing hex. But it turns out memory allocations are definitely a much more expensive operation than spending some more CPU cycles on this. But certainly it is still something, as we can see in the profiling data, it's still quite a considerable amount of time that we're spending here, right? So it's almost maybe a quarter of time that we're spending in here. So we can definitely still optimize this quite a bit. Okay, great question though. I agree. In the shape that it is right now, we probably wouldn't necessarily want to leave it in. But I think the last thing that I want to have a look at today, and then maybe we can call it a day for today. Let's check out this scanner if there's something that we can improve here. You can see scan lines, that does a search as well. Do we really need a scanner? I wonder if like no, this is actually a tab 2. Hopefully this is still readable. Maybe a buff.io reader would already be sufficient. And then we do something like read slice. Perhaps we can commit where we're at, so we can return to this point. So nice. So let's have a look at this. I'm not going to dig too much. I'm just going to see if we can replace this scanner with something a little bit more simple. So let's try this reader. All we're doing is reading a file, right? We don't really care about anything else. Cannot convert FD variable to type. We probably need to do like new reader or something. Like the zero? Okay. Now, okay. Now we do we don't do a for condition, and instead we read it within this. So we do, yeah, right, read bytes. I think read bytes allocates, if I remember correctly. Yeah, it allocates a new buffer to read. That's not what we want to do. We want to do read slice. Read slice, I believe, is the thing we're looking for. Read slice reads until the first occurrence of the limiter in the input, returning a slice pointing at the bytes in the buffer. That's exactly what we want. We want the bytes of the underlying buffer. The bytes stop being valid at the next read. That's exactly what we want here. All right, let's try this. We're gonna not read bytes. We're gonna, my language server is blocking me. Read slice. Yeah, if this is an EOF, we want to break out of the for loop, and otherwise we return the error. All right, that looks good. We already get an error. I think we're good. We should be able to look here. Alrighty, let's see. Okay, I'm not sure there's a big difference. We might need to benchmark our two approaches again. Oh, well, no, actually, that did make quite a bit of difference again. Interesting. have to look at the profiling data to understand why. What kind of buffer does it allocate? I wonder. New reader just returns a reader with a size, and it uses a default size of 4096. That's probably quite reasonable. Most page sizes, like the page size in Linux is typically 4K, so it's even like aligned with page size. So this sounds pretty good as a default. Might also be why all of this is working quite well for us. I think this is good, and it makes sense why it's faster. Now, are we still conf t slice make slice? Now we're seeing make slice show up a little bit more again. I wonder, usually these files are sorted. So sorted by end address. So maybe we can avoid even sorting if it's already sorted. You know, if did we have the Linux curve map interface? Larger. It looks like this does not define anything about sorting. Maybe sort slice also checks first. No, it doesn't look like it. I think most of the time this should already be sorted. So I want to say we might be able to do something like if not sorted. What was it again? Yeah. All right. We'll let it slide. So if end -1 is larger than, yeah, this is true. This is correct. All right. Let's see. 2115, 2134. There's probably no change here. Let's have another look at profiling data. All right, so it looks like we're still sorting, so it's not actually helping us. It seems to be very, very fast to check whether it's sorted. But looks like this is not helping us. Shame. All right. Nevertheless, let's see what else we can see in this profiling data. But we're already 20% faster. That's quite significant. Yeah, I think we're just about optimal. I think the only way we could get better is by further improving this parse uint function to be only for hexadecimal integers, like text that is representing integers in hexadecimal. That would also make this function, like it was mentioned in the comments, it would make the function much more maintainable, because right now it handles really a lot of cases, and we could be much more focused. But I think I'm gonna leave it at this for today. I think we did quite a lot. Maybe I'll take some time in the coming days to let me remove this. And maybe in the coming days I'll kind of still clean this up and fix it and only handle hexadecimal numbers. But I think 21% is definitely quite a huge improvement. So yeah, quite a successful stream once again. Thanks for everyone who joined us live today, and hopefully plenty of y'all are catching the recording. Let us know what future episodes you want to see, what software you want to see being optimized, if there are anything else about software performance that you would like us to showcase. Let us know at polarsignals.io on Twitter, or you can reach out directly to me as well at Fred Branch on Twitter. You can join our community Discord. If you go on the polarsignals.com website, you can scroll all the way to the bottom. In the footer, there's our Discord channel. Always happy to see people there. Let us know if you have any questions about Polar Signals, Polar Signals Cloud, Parca. Yeah. All right. Thanks everyone for stopping by, and have a wonderful local time. See y'all next time.